मंजर है ये नया।
Okay, mute yourself, Shoham. So what I was telling in the last session, probably we can all hear me now, that I'm going to start this section, linear dependence and linear independence, and I'm going to read the section for you from here in this book. And then I'm going to talk about this a little bit. After that, the class will be done with the class for today. So my linear dependence, what is that actually? After learning about the linear combination and spanning sets, linear dependence and linear independence, this thing is very important. Okay, so what is written? Suppose that V is a vector space over an infinite field, and that W is a subspace of V. Okay, unless W is a zero subspace, W is an infinite set. It is desirable to find a small finite subset S that generates W, because we can then describe each vector in W as a linear combination of the finite number of vectors in S. I mean, what they are doing, you can draw a big circle, which you can consider a vector space, and inside that circle we have another circle contained in V that is called W. Now W being a subspace of the vector space, inside the W, you are again trying to find another smaller set, which is a subset of W, and that set S, the elements of that set is actually will try to generate the subspace W of the vector space. So when mathematicians deal with a big set, then they try to concise, they try to compact their results. Okay, make the results compact in a smaller subset. And they always say that if I can deal with the small set, then I can deal with the bigger set. And if I can say something about the smaller subset, then we can give some our comments on the bigger subset. So therefore this analysis they do often in various mathematical topics. Okay, so for example, they have considered the set R3, the vector space R3, and you know the R3, the points of R3 will be all triplets, and therefore from there they have selected 4 points: 2 1 2 minus 1 4, 1 minus 1 3, 1 1 minus 1, and 1 minus 2 minus 1. These 4 points have been chosen from R3. Okay, and not only from R3, not only from W, they have been chosen from the set capital S. Okay, after that they have done some a bit mathematical calculations over here, and they have shown you can do the mathematical calculations by yourself, that they have said that the vector U4, this vector is a linear combination of other vectors in S if and only if they want to check actually whether this vector, they have arbitrarily selected this vector U4, and they want to check whether this vector U4 can be expressed as a linear combination of the remaining 3 vectors, U1, U2, and U3, just like we did in the previous class. So they have selected scalar quantities A1, A2, A3, and they tried to express U4, the vector U4, in terms of these scalars U1, U2, U3. Okay, so they have written U4 equal to A1 U1 plus A2 U2 plus A3 U3. After that, by comparing the coordinates of both sides and by using coordinate wise addition and scalar multiplication, they have got 3 equations in terms of A1, A2, A3. Okay, and after solving these equations, and then they tried to find the solution of this equation, and they have found that this set of equations with 3 unknowns, this set of equations with 3 unknowns has a solution actually. Just like we found the solution in the previous case, this set of equation has a solution. They could find the values of A1, A2, A3 actually. So they have left this particular section for you. And you can do it. You can also do it by yourself. That it can be shown that in fact U3 is a linear combination. This doesn't However, I mean, they have shown that U4 is actually not a linear combination of these vectors U1, U2, U3. You cannot express U4 as a linear combination of U1, U2, U3. But on the other hand, they have shown that U3, the vector U3, according to their choice, can be expressed as a linear combination of the remaining vectors U1, U2, U4. And this is the solution, which you can do by yourself. This is the solution, okay? So U3 can be expressed as 2U1 minus 3U2 plus 0U4. You see that actually the vector U4 is getting redundant. There is no vector in U4. Okay, the vector U4 is not actually required to express the vector U3. So U3 is actually represented in terms of the vectors U1 and U2. And therefore, if it is so, then by this particular operation that U3 is expressed as in terms of U1 and U2, we can change the sides and we can write this as minus 2U1 plus 3U2 plus U3 minus 0U4 is equal to 0. So actually you see that zero vector, if it is so, then zero vector of the vector space has been, my vector space in this particular example is R3, has been expressed in terms of the linear combination of the four vectors U1, U2, U3, U4. So that is also a kind of checking. If we can check, but the interesting point here is that we have successfully expressed the zero vector. We have successfully expressed the zero vector as a linear combination of the four vectors U1, U2, U3, and U4. But not all the coefficients here are zero. Not all the coefficients of the vectors here are zero. Say for example, U1 has got a non-zero coefficient -2, U2 has got the non-zero coefficient 3, U3 has got a non-zero coefficient 1, but U4 has got a zero coefficient 0. So if I combine them together, the zero vector comes. So we can get result 0. So whenever you write 2x minus 2x, okay, so whenever you write 2x minus 2x, so the coefficients in both these things are not actually 0. One coefficient is 2, another coefficient is -2. But if we add them together, we get the result 0. So therefore, it is in vector spaces, it is often seen that to get the zero result, zero vector, we don't have to consider the zero coefficient always. We can consider the non-zero coefficients. Some coefficients may be 0, some coefficients may be non-zero, but the resultant thing will always can be 0 also. So from this particular observation, they have tried to define something which is very important for further study in the vector space, and the result is a subset capital S of a vector space V is called linearly dependent if there exists a finite number of distinct vectors U1, U2, UN. All these vectors are distinct from one another. You cannot consider that some of the vectors are same. All these vectors are distinct, and we have to consider a finite number of vectors in the set capital S. And scalars A1, A2, AN. These scalars are not all 0. Some scalars may be 0, some scalars may be non-zero. All scalars may be 0, like maybe non-zero like this. Not all scalars are 0, such that if we can express the zero vector in this form, the A1 U1 plus A2 U2 plus ... plus AN UN equal to 0, in this case, the vectors in the set capital S, these vectors are actually called linearly dependent vectors. Just like in the previous case, they have tried to, you have shown that, you have seen above that the vector U3 has been expressed as a linear combination of the vectors U1, U2, U4. And since the vector U3 has been expressed as a linear combination of the vectors U1, U2, U4, so, sorry, Mike, just a minute. Since the vector U3 has been expressed as a linear combination of the vectors U1, U2, U4, this implied that the zero vector has been expressed actually in terms of, zero vectors have been expressed in terms of the vector linear combination of the vectors U1, U2, U4. Okay. just like U3 has been expressed as a linear combination of this. So from this, they have deduced that 0 vector has been expressed as a linear combination of these 4 vectors. But here, not all the coefficients of the vectors are 0. Some coefficients are 0, some coefficients are non-zero. So if I get such a situation, then we'll say that these vectors U1, U2, U3, U4, these vectors are linearly dependent. These vectors are known as linearly dependent vectors. And if we combine these vectors in a set, that set is actually called the linearly dependent set, LD set. For any vectors U1, U2, UN, we have this if A1 equal to A2 equals to AN equals to 0. Now, it is pretty obvious that A1, U1 plus A2, U2 plus AN, UN equal to 0, there is always a trivial solution that if individual coefficients are 0, then also the result is 0. So this representation is called the trivial representation. Okay, but in the linearly dependent set definition, they are not talking about the trivial representation. They are talking about the non-trivial representation where not all the coefficients are 0. Okay. Any subset of a vector space that contains the 0 vector is linearly dependent. So if I in the chapter 1.2, there was an exercise which talked about that singleton 0 vector is a vector space. So we know that a vector space, a set containing 0 vector only is a vector space. I asked you to try that particular problem. So that vector space, if I consider, then this 0 vector is also linearly dependent, because for 0 vector, we can find a non-zero scalar coefficient, any non-zero scalar coefficient, which when multiplied by the 0 vector gives you the 0 vector. So this representation is a non-trivial representation, and therefore singleton 0 vector is an LD set. Remember this. Now, here they have considered another example where four tuples have been considered, and they tried to express the 0 vector in terms of these 4 vectors. So they considered 4 scalar coefficients A1, A2, A3, A4. And from this, they have deduced the equation. They have deduced this equation, and this equation, after solving this equation, they have found that A1 equals to 4, A2 equals to -3, A3 equal to 2, and A4 equal to 0. And there, since the values of A1, A2, A3, these are non-zeros, so this set containing these 4 vectors, they are linearly dependent set. So it is an example. Below they have shown another example in terms of matrices. Okay. After that, they have defined the linearly independent set. And linearly independent set is just the complementary to the definition of linearly dependent set. So they have written that a subset capital S of a vector space that is not linearly dependent is called linearly independent set. Okay, so that's why I kept on saying that the knowledge of linear dependence and linear independence, they are complementary to one another. Okay. A few examples, a few special cases, like in question number in this one, they have said that the empty set is linearly independent set. Why is it so? If we consider that empty set is not linearly independent, then what does it mean? Since linearly independence and linearly dependence are complementary to one another, so if we consider that empty set is not linearly independent, that must be linearly dependent. And for linearly dependence, the empty set must contain a vector, because you have to show that for that vector, there exists a non-zero scalar for which that holds scalar multiplied by the vector becomes 0 vector. But LD set, if we consider empty set to be not linearly independent, then that means it is LD, and that means it contains it must contain a vector, which is not true. Which is not true, because empty set is empty set, it doesn't contain anything, and therefore it must be LI, linearly independent set. Now, if you consider any, in the previous case, we have considered the 0 vector space. I mean, the vector space containing only the 0 vector, that was LD. But if you consider any vector which is any singleton set where only one vector is present, say U, as they have mentioned U, then this singleton set, singleton vector, is it a is it a linearly independent or linear dependent? So if we call that this is not linearly independent, this is linearly dependent, then there must exist a scalar quantity A, which is when multiplied by the vector u gives you the zero vector. So AU becomes zero vector. Now you multiply, since A is non-zero, we can express the vector u in this manner. We can express the vector u in this manner. We can write it as A inverse into AU. Now A inverse into AU means what? We have already got AU equal to 0. So A inverse 0, this gives you 0. So U is actually becoming the zero vector. U is actually becoming the zero vector, and therefore, but this is not, it contradicts our assumption about U. We actually considered U to be non-zero vector, and therefore this particular set cannot be linearly dependent set. Okay, and hence singleton vector singleton U is a linearly independent set. And lastly, if you ask me that, okay, to check that the vectors u1, u2, these vectors are linearly dependent vectors, then we can consider the vectors, we can consider the scalars, and we can multiply them together, adequate it to the zero vector. And if we can show that some of the vectors are non-zero, some of the vectors are zero, then the set of vector is LD. What is the checking criteria? That if we want to show that these vectors are not LD, these are LI, what are the checking criteria? This checking criteria is given in this particular point. They have said that a set is linearly independent if and only if the representation of the zero vector is trivial representation. That means if you want to show that a set of vectors is Li, then you have to consider scalars, you have to consider their linear combinations, you have to equate the linear combination to the zero vector. But after solving, if you find that A1, A2, A3, all these scalars are zero scalars, then that means this particular set of vectors is linearly independent vectors. And after that, they have shown one example in 3. Very easy example. They have considered the set of vectors S here in this particular case, and they have showed that if I consider their linear combination in the following manner, then this particular the equations which I get are of this form, and from there we can easily solve that A1 is 0, A2 is 0, A3 is 0, and after substituting all of these, we find A4 equal to 0. And therefore, this set of vector is a linearly independent vector. And example 4 is very important. Look at this example 4. Do you want me to discuss example 4? I can read it for you, but if you want me to do the board work, if you can understand this example 4, then I don't need to do the board work. Otherwise, okay, let's see what example 4 is saying. They have considered the vector quantity k, and it is taking different values 0, 1, 2 up to n. Okay. Now, when k equal to 0, I'm reading it, but you just do it in your copy. When k equal to 0, we get a polynomial of this form. So it becomes P0x. Put k equal to 0 over here. So we get P0x. And P0x becomes x to the power 0, which is 1. So we get 1 plus x to the power 1, because 0 plus 1 is 1. So 1 plus x square dot up to xn. So this is the polynomial P0x. When I substitute k equal to 1, we get polynomial like x plus x square plus dot up to n. If we substitute k equal to 2, we get polynomial P2x as x square plus x cube plus dot up to x to the power n. If we substitute k equal to n minus 1, we get x to the power n minus 1 plus x to the power n. And lastly, for k equal to n, we get the polynomial Pnx, which is x to the power n. Okay. We have considered all such polynomials in the set given as follows. So we have considered the polynomial P0x, P1x, Pnx together. And this polynomial x, this set of polynomials, you know that polynomials are actually all these individual polynomials are members of Pnf. PNF is the set of vector space of all polynomials of order less than or equal to n. So this set, I want to show that, I want to check whether this set is linearly independent or not, for which they have considered scalar quantities a0, a1, dot, 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 an, and they have placed this equation over here. And after putting the forms of these polynomials and equating and combining the like terms, constant terms and the terms containing the x to the raised to the power 1, term containing x square, they have got this set of equations: a0 plus a01, a0 plus a1x plus a0 plus a1 plus a2x square, and so on. From there, and on the left hand side, do not write 0, 0, 0, 0. On the left hand, since we are talking about polynomials, so on the left hand side, the zero vector will be of the form 0 plus 0 into x plus 0 into x square plus 0 into x to the power n, and so on. The right hand side is not the ordered n tuple 0. Remember this. Right hand side, this part is actually the zero polynomial, which is spanned by the set 1x, x squared, dot, 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 up to xn. So if I equate the like powers from both sides, so the constant quantity 0 is equated to a0. From 0x, the coefficient of x, which is 0, it is equated to a0 plus a1. Coefficient of x square is equated to a0 plus a1 plus a2. Coefficient of x to the power n is equated to a0 plus a1 plus dot, 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 an. And from this, you see, you can easily solve that all these quantities are actually 0. All these quantities are actually 0, and therefore this set of all these polynomials is a linearly independent set. So this example is very important, and this theorem is also very important. They have left this particular theorem for you to prove. I shall end my today's session and by stating these two theorems, which are very important. The theorem is saying that if V is a vector space, and if we get subsets of this form, S1 subset S2 subset V, means S2 is the bigger subset which contain the smaller one, and if you can show that the smaller subset is linearly dependent, if this smaller subset is linearly dependent, the bigger one will also be linearly dependent. And if you can show in a similar situation, if you can show that smaller subset is linearly independent, a bigger subset is linearly independent, the smaller subset is also linearly independent. These two results are very important for solving the problems of vector space, which we have in our further chapters, in the later chapters. Okay, so if we are actually considering a circle which is S2, and inside that circle you are getting another circle which is S1 contained in S2, but if you can show that the inner circle is LD set, outer circle will also be LD set. Okay, if the smaller subset is linearly dependent, outer one will also be linearly dependent. But in a similar situation, if you can show somehow that if the outer circle is linearly independent, the inner circle will also be linearly independent. This result is extremely important for studying vector spaces problems, which we have in our further chapters. Okay, so with this, I'm going to conclude my today's unofficial session where attendance has not been taken. It is not an official class. The students only were there because we wanted to discuss a few problems, okay, from our known sections, very important problems which I needed to discuss. I couldn't have left this for you. And thanks for your participation in today's class. I shall upload the video in the YouTube, and from there the students who were not participating, or because of today is actually the holiday and they couldn't participate, they had some plans, so they can watch this video in the YouTube. Okay, so this video is just, always tell your friends that this is an unofficial class, it is not official class, and attendance will not, today's classes attendance will not be counted. Okay, so with this I'm going to end my today's session. Thank you so much, and in advance, Happy New Year. We shall meet again in the next year 2021. Till then, bye.